Hey, 7th grade. It's Miss McGowan. I'm getting ready to teach you your next math lesson. Before I start, I wanted to take just a moment to do a couple of reminders, things that have just occurred to me that I might need to mention to you guys. First of all, iReady versus the book and the videos. Okay, let me talk about that really quickly. If you are doing the assigned lessons on statistics and probability that I assigned for every kid before I left work on iReady, then you do not have to do the book with the YouTube videos with me. If you're choosing to do the book lessons with the YouTube videos where I'm teaching you, you do not have to do iReady. You can do one or the other. I have a checklist. I'm keeping up with it. I'm going in and looking at kids that are passing iReady lessons or kids that are sending me pictures of work from the book. I'm taking care of you on that end. If you want to do both, if your parents want to push you and have you do both, that's fine. No one's going to be mad at you for doing extra, but you only have to do one or the other for your grade, okay? If you are doing the book and the video lessons, don't forget to send a picture of your work through Remind to me. That's how you get your grade. Also, if for some reason you do not have your math book with you, nor do you have a packet that has a copy of the lessons, you can always follow along with me on notebook paper and send me a copy of that. I have several students that are doing that, and it's been fine. The other thing really quickly is just Remind. If you'll look at your previous messages from me, you'll see all of your teachers' codes in a picture that I've sent out a couple different times. Please make sure that you've joined all of your classes on Remind, okay? We're trying to get 100% of you, and there's a lot of you, so please make sure and do that for us, okay? All right, so today's lesson is Chapter 9, Lesson 4, and it's on simulations. We're going to be on pages 744 and 745 from our math book, and all you're going to need today is a pencil. And today's lesson has little to do with number crunching, math, things like that. It's more situational type math. I'm not even going to give you guys an extra practice page to try on your own. I just want to expose you to this concept, and hopefully you'll get an understanding of that, okay? So let's start with what a simulation is. Those of you that like to play video games probably have heard this term before or kind of have an idea of what a simulation is, or if you've done any kind of VR stuff, virtual reality stuff, you know that simulations are sort of like, it's kind of like faking the real thing, sort of. The math book defines it as experiments that model the probability of real life events, okay? So we can use simulations in math to represent the probability of certain events happening, okay? It's almost like being able to predict the likelihood of something happening by creating a simulation or kind of a model of that event, okay? So that's what we're going to look at today. Typically, when we're creating simulations, you, especially for the purpose of 7th grade math, you'll see a lot of things like simulating an event by using a number cube, or by flipping a coin, or spinning a spinner, or using this many blue marbles and this many white marbles, okay? Really, really simple representations of real life events. And we're going to use really simple representations today. To introduce the concept to you like I normally do, I'm going to do two different super simple simulations for you. The first one is going to simulate Mr. McGowan going to work. So every day he gets up, gets dressed, puts on his slacks, he's a teacher too, puts on his dress shirt, and then he has to choose a tie. Now, we're going to say that he has 6 different ties that he can choose to wear to work. And I want to create a simulation to figure out how many days of work he would have to go before he had worn all 6 ties. This is assuming he can wear the same tie 2 days in a row, okay? So to simulate this, to simulate the probability of this, what I've done is I've made me a little tally chart right here on the board to represent tie 1, tie 2, 3, 4, 5, and 6. These represent the 6 different ties, okay? I found an old game piece from one of the kids' games because I'm at home and my materials are slim, but typically I could use a number cube that's numbered 1 to 6. And I went in, I don't know if you can see with my Sharpie, and I actually numbered each side 1 through 6. So here's how we're going to simulate this. Again, I'm wanting to figure out how many times, if he randomly chooses a tie to wear to work, how many days of work would it take before he has worn all 6 ties? Now, before we start this, it's important to say, a simulation, the more times you do it, the more accurate your results are going to be. We're going to do this once. If we turned around and did it another time, we could get a completely different answer. So what you would want to do if you were like a scientist or some kind of statistician, you would want to repeat these simulations hundreds, maybe thousands of times and get an average result, okay? But to just kind of introduce this concept to you, what I'm going to do is I'm going to roll this. And every time I roll it, I am going to tell you guys which tie I'm getting, and I'm going to tally it right here on my little chart. And we're going to see how many times it would take for all 6 ties to be randomly chosen to be worn to work, okay? So I've got 5. I'm going to do this quickly. 2, 6. So far, so good. 1, 4. And 3, okay? I can't believe that worked out that well. So based on this simulation, in 6 days, he would wear all 6 ties. Now let's try it again. This is me going off the grid. I wasn't planning on doing this. Let's do it again just to see what happens this time, okay? So according to this first trial, it would take 6 days for him to wear all 6 ties. Okay, let's try it again. So there's 4. 6, 6 again, 1, 3, 4, we need 2 and 5, 6 again, 6 again, 5, and now I just need to roll a 2. 5 again, 6 again, 4 again, 1, 5, and 2 finally, okay? So according to this simulation, this time it would take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 15. It would take 15 days for him to wear all 5 ties, okay? So if we wanted like a really, really accurate representation of this, we would do this simulation lots and lots and lots of times and then get an average of them, okay? But this just kind of shows you how you can simulate a real life situation. Now, let me show you another way it can be done. We can actually be given probabilities, percentages, chances of something happening, and then use it to simulate the probability of an event happening based on those statistics. So here is an example of that, okay? We're going to say that there is a 60% chance that it's going to rain for the next 2 days, okay? Well, if I simplify 60% into a fraction, 60/100ths, we know that reduces to 6/10ths or to 3/5 in simplest form, okay? So 60% chance can be also thought of as a 3 in 5 chance if we're looking at a fraction, okay? So what that means is if we were going to put our rain chances into a simulation, I know that if there's a 60% chance, 3 out of 5 possible outcomes should represent rain. 2 out of 5 possible outcomes would represent no rain. Okay, so what I've done here is in this little bowl, again, using what I can find around my house, I have 3 silver jacks and 2 gold jacks. The 3 silver jacks are going to represent rain, the 3 in 5 chance or 60% chance that it will rain, while the 2 gold ones will represent no rain. Now, according to this statistic, there's a 60, or this probability, that there's a 60% chance that it's going to rain the next 2 days. If we wanted to simulate the likelihood of this being correct, what we could do is we could draw a jack where, again, the silver represents rain, the gold represents no rain, for the next 2 days and see what happens, okay? And I'm going to do 3 trials of this, okay? So I'm just going to randomly choose. So the first day, that is rain. I'll just use a check mark. I need to put that back in there to keep it. All right. And then I have rain again. Okay. Now, let's do another try. So on day 1, try not to look, keep it random. We have rain. On day 2, I have gold, so that's no rain. All right. Let's do one more trial. No rain. Rain. Okay. So there are the results from my simulations using a 60% chance or 3 in 5 chance that it's going to rain the next 2 days to actually test that out and simulate it, okay? So I'm going to get my math book set up. Again, this lesson is going to be just you listening, following along, and getting the concept of what a simulation is, and hopefully developing an idea of what a proper simulation would be to represent certain situations. For example, flipping a coin wouldn't necessarily be a great simulation for the 6 different tie choices, right? Because the coin only has 2 different outcomes, and we needed something with 6 different outcomes. You know, or for the rain chance, we wouldn't have wanted to flip a coin for that because that would have been 50-50. And we needed to represent a 60% chance of rain versus a 40% chance of no rain. So you want to make sure that your simulations sort of line up with the possible outcomes represented in your situation, your probable situation, okay? So I'm going to get set up with the book, and we'll go through and do a few problems together on that. Okay, so here we are back in our math book on page 744. I have 7 different situational problems chosen for us to complete together, where we are either performing a simulation or choosing an appropriate simulation that could be used for that situation. Again, because we're in the 7th grade, we're going to be using things like spinners, number cards, number cubes, spinners, again, marbles, flipping a coin, that kind of stuff, okay? Marbles, it's easy stuff to get our hands on. All right, so number 1 says, an ice cream store offers waffle cones or sugar cones. Each is equally likely to be chosen. Describe a model that could be used to simulate the situation. Based on your simulation, how many people must order an ice cream cone in order to sell all possible combinations, okay? Well, in this situation, we have 2 different outcomes that we want to represent, a waffle cone and a sugar cone. What is something that we can think of that could easily represent 2 possible outcomes? Flipping a coin, okay? So we're going to say that our simulation would include tossing a coin, okay? Now on this, not only do we need to tell what our simulation was, we need to actually carry it out. It wants us to figure out, if this were the case, how many ice cream cones would have to be sold until you had a waffle cone and a sugar cone that was sold. So let's do this. Let's say heads represents a waffle cone and tails represents a sugar cone, okay? And I'm going to flip this coin right here underneath my little setup, and we're going to see, according to this simulation, how many cones would have to be bought in order for each one to be sold, okay? So we've got a heads there. Got another heads. We've got another heads. Another heads. And finally a tails, okay? So according to this simulation, it looks like it would take 1, 2, 3, 4, 5 cones being bought before both the waffle cone and sugar cone would be sold. So we're just going to say how many people must order an ice cream cone in order to sell all combinations? 5 people. Now again, these simulations would need to be repeated lots and lots and lots of times, numerous times, to get an accurate representation. But today, just wanting to kind of give you the concept of what a simulation is and how it works. Number two says an electronics store has determined that 45% of its customers buy a widescreen television. Describe a model that you could use to find the experimental probability that the next 3 television buying customers will buy a widescreen television, okay? Well, first of all, we have to understand what this 45% right here means, okay? This 45% chance means 45 out of 100, okay? And if we simplify that by reducing both the numerator and denominator by 5, we're going to get a 9 in 20 chance. Now, here's what we have to understand. We have to understand that that 45% chance means 9 out of 20 people would buy that widescreen television. But what that also means is that the other 11 out of the 20 would not, okay? So we need some kind of simulation that represents 9 that would buy a widescreen television versus 11 that would not. And I'm just using the check mark to represent they would buy the widescreen television and the X to represent they wouldn't. 9 out of 20 will buy it, which means the other 11 people will not buy it. That equates to our 45% chance. So to simulate this, what I could do is I could take 20 marbles and I could put 9 red marbles in there to represent buying a widescreen television. And I could put 11 white marbles in there to represent not buying one. And then I could randomly draw a marble 3 times to see the likelihood that the next 3 customers would buy the flat screen, widescreen television. Again, it would need to be repeated numerous times to get accurate results on that, okay? So just to jot that down, we're going to say that our model could include using 20 total marbles, where 9 represent buying a widescreen and 11 don't. And then what we would need to do is we would need to draw 3 marbles to simulate the purchases of the next 3 customers. Okay? So, that's what we're doing here. All right, let's move on to the next page, 745, and let's do a few more of these. On 745, number 1 says, the questions on a multiple choice test each have 4 answer choices. Describe a model that you could use to simulate the outcome of guessing the correct answers to a 50-question test, okay? So first of all, we need something, since there's 4 answer choices, we need a simulation that would have 4 possible outcomes. One thing that I typically think of is like the 4-color spinner, where you kind of thump the little spinner and there's 4 different sections to it. So spinning a spinner with 4 sections could simulate this. Now, the second part of this is, if we're wanting to simulate a 50-question test, then we would want to spin this 4-section spinner 50 times and record what we get, and then compare that to the actual correct answers to see what the chances would be of those actually lining up. So we could spin a spinner with 4 sections 50 different times. Okay? Number 2, a game requires drawing balls numbered 0 through 9 for each of 4 digits to determine the winning number. Describe a model that could be used to simulate the selection of the number. So this makes me think of like, kind of like when you see them doing the little balls on the TV for the lottery, the winning lottery numbers. So they need 4 different digits, and those digits can be anything from 0 to 9, okay? So one thing that you could do there is you could do a random number generator in your phone. I know that I have an app on mine where I can set it in a range of numbers. So I could set my range from 0 to 9, and then I could randomly generate 4 numbers that range anywhere from 0 to 9 to see what I get. Another easy thing to do would be to use, and this is the one I'll jot down, use number cards from 1 to 9, randomly choose 4. You could also use a deck of cards where ace represents 1, and maybe like a joker represents a 0, and then cards 2 through 9, and randomly mix those up and choose 4 from those. Anything that you had 9 possible outcomes and you choose 4 from could simulate this situation. Number 3. Okay, it says on this one, a jar of cookies contains 18 different types of cookies. Each type is equally likely to be chosen. Based on your simulation, how many times must a cookie be chosen in order to get each type? Okay, so if we were going to do this one, we would need something with 18 different types of cookies. Now, there's not a whole lot of general things that come to mind that have 18 outcomes. But one thing that I did think about that we could use that would generate 18 outcomes is the combination of a spinner that has 3 equal sections on it and a number cube which has 6 different sections. If you remember back to our lesson on sample space, you can use the fundamental counting principle and multiply the number of outcomes in each event to get a total number of outcomes in the sample space. So if we wanted to use a 3-part spinner with a number cube that has 6 different outcomes, that would give us 18 different outcomes. So we could spin the spinner, we could toss the number cube, and each part of the spinner with an individual number could represent a type of cookie. And then what we could do is we could keep track of all those combinations until we had actually spun and tossed the spinner and number cube enough times that each combination of cookie had been chosen. Okay, so that's kind of abstract. It's using more than one object to simulate the situation, but the lesson wanted you to know that that was possible. Okay, so we're going to say that we could spin a 3-part spinner and toss a number cube That would give us 18 possible outcomes to represent 18 cookies. Then we would need to repeat this simulation until all possible combinations had been obtained. Okay. Number 4, a cooler contains 5 bottles of lemonade, 4 bottles of water, and 3 bottles of juice. Each type is equally likely to be chosen. Based on your simulation, how many times must a drink be chosen in order to get each type? So this was kind of like doing the tie simulation earlier, okay? We've got 5 bottles of lemonade, 4 bottles of water, and 3 bottles of juice. If we just randomly reach in that cooler and grab out a drink, we want to know how many times would we have to reach in and grab until we had chosen each type. So we could simulate that in lots of different ways. Because there are 5 bottles of lemonade, 4 bottles of water, and 3 bottles of juice, because there's not the same number of chances for each one, we have to look at each one of those as a separate chance. So that's a total of 12 different opportunities. 5 of those 12 being lemonade, 4 of those 12 or 1/3 being water, and then 3 bottles or 1/4 of the 12 being juice. Okay, so in order to simulate this, what we could do is we could take and we could put, we could do marbles. Marbles would be easy on this one, or kind of like I did with the jacks with the rain chances. We could use 5 yellow marbles to represent the lemonade. We could use 4 white marbles to represent the water. And we could use 3, we'll just do green marbles to represent the juice. So we could use 5 yellow marbles, 4 white marbles, and 3 green marbles to represent each of the different types of drinks, okay? We could combine those in a bowl, in a cup, in a bag, and randomly reach in and choose a marble, keeping tally of which drink it represented. And then see how many tries that would take until we had taken out a yellow, a white, and a green, okay? So we can use 5 yellow, 4 white, and 3 green marbles. And then we want to repeat choosing a marble and replacing it. That's really important that you replace it until all colors have been chosen. All right, last one. Number 5, players at a carnival game win about 30% of the time. Based on your simulation, what is the experimental probability that the next 4 players will win? Okay, well on this one, we've got to think about what 30% represents. 30% means 30 out of 100, which is the same as 3 out of 10, okay? So that means 3 out of 10 or 30% win, I'll use a check mark to represent winning, versus the other 7 out of 10 or 70% that lose each time. So in order to simulate this, if we want to know what the chances are of the next 4 players winning, we could do a simulation that has 10 possible outcomes, okay? Let's use marbles again. That's really easy. You could use a spinner. There's different things you could do, okay? But the marbles are just really easy to simulate, okay? So we're going to say that we could use 3 red marbles to represent the 3 in 10 chance or 30% chance of winning, and 7 blue marbles to represent the 70% chance of losing, or the 7 in 10 chance of losing, okay? And then we would want to randomly choose a marble and replace it 4 times to represent the next 4 players, okay? So if I reached in and I got a red and 3 blues, that means my next 4 players would get a win, a loss, a loss, and a loss, okay? Now, here's what I want to say about this. This is not number crunching type of math, okay? This is probability. And this lesson today, I'm not even going to assign you any of the extra practice to try on your own, because really more so than anything, I wanted just to expose you to what a simulation means and hope you have a little bit of a basic understanding of different ways that you can represent real life situations happening in order to make predictions or to model possible outcomes. What you do need to know about real life simulations is that they have to be conducted over and over and over and over to be valid and to be accurate. They would need to be done hundreds, if not thousands of times, with the outcomes averaged together, okay? So you guys can snap a picture of these practice pages that we've done together, and that will take care of your first lesson for the week. All right, talk to you guys soon. Bye. Hey, 7th grade, this is my 1-minute disclaimer to the video that I just did for you guys. I was going back and watching it like I normally do, and I found 3 mistakes, and I tried to let it go. I can't even say I didn't for a second think about redoing the video, but it just takes so long and so much work. But I want to mention to you 3 mistakes in case you noticed them and was wondering. The last thing I want to do is confuse you. On my 2 examples at the beginning, on the tie example, I think I said 5 instead of 6 one time. Should have been 6. I verbally said 5. And then on the jacks, when we were doing the 3 and 5 or 60% chance of rain, on the last trial, I did not take that silver jack and put it back inside the bowl before I chose for day 2, and I should have. For these simulations to be accurate, you have to keep the percentages and the chances the same each time. So whenever I pulled that jack out, I should have put it back inside before I chose the next one. And then the last thing that I noticed was when we were doing the problem on the number cards, or choosing a number randomly 4 times from numbers 0 through 9. It was number 2 on the 2nd page. I wrote down 1 to 9 in our answer, and it should have been written as 0 to 9. So I just wanted to clarify that with you guys in case any of you, as you were watching the video, were kind of like, that didn't seem right. Hopefully that'll clear you up. Thanks, guys. I'll do better next time. Bye.